Okay, so let's go ahead and take a look at problem 8. It has a few different subparts, a couple on volumes of known cross section, and a couple of revolutions. Um, we'll kind of just see how I can lay this out. I didn't like my previous presentation as well, so I kind of wanted to look at it again. So I'm actually taking another pass at this. So we are going to have this region right here, a nice simple parabola, 3x squared, intersecting this horizontal line y equals 27, going like this. So I set them equal, and I found out that that happened at both 3 over here, 3 comma 27, and -3 by symmetry, right? So I am going to be sliding those across, and you can see that I would find the volume by doing the area of that triangle multiplied by some kind of a dx, right? So I'm going to do the area of the triangle multiplied by some dx, integrating over the span. That integration is that it's a sum of all of those things put together with infinitely thin little pieces or partitions. So let's just see what we can do. So I started by thinking about what is this cross-sectional triangle. And so when I looked at it, the distance from here to the curve right here is some kind of a y value, which means the distance from here to this is 27, which actually means the length from here to here is actually 27, take away the y value that is involved. Let me scoot that over a little bit so I have enough room to write it. So this is 27, take away y. Now, the thing you have to be a little bit cautious about is this is not a simple right triangle, of course, it's an equilateral triangle. So how we have historically handled equilateral triangles is we would take this portion and cut it in half, which means this one right here would be, this portion would be 27 minus y cut in half. And because this is a 30, 60, 90 triangle, that makes the height of it 27 minus y divided by 2 multiplied by the square root of 3. Now that looks pretty gross, and it really truly is. So when I go out this thing and actually try to figure it out, I'm going to integrate 1/2 the base, which is 27 minus y, times the height, which is 27 minus y, divided by 2 times the square root of 3, times the thickness, which is dx, evaluating that from, I'm going to go from 0 until 3 with a double on it. Now, again, this works perfectly fine. There's a couple little things we could do, like I could cancel out those 1/2s. I could take this root 3 over 2 because those are constants and I can pull them to the front. And what you're going to notice is that if I did pull these pieces out and put them in the front, then I have a 27 minus y times an additional 27 minus y, which isn't so bad. And so one last little trick that I'm going to pull is that if we replace y with 3x squared, we are ready to go. And one thing that you'll notice as we do that problem, now again, we could distribute that out, but I think for the sake of brevity, I'm going to go ahead and let my calculator do a little bit of this real quick because I don't want the video to be too long. We do know how to distribute this out. We do know how to do the power rule, etc. But let's see what we can do. So you're going to notice that I'm, for the moment, going to ignore that root 3 over 2 that's sitting in front. And let's go ahead and insert a parentheses here, insert a parentheses here with a square and a dx. And let's have the calculator give me that as a fraction. So I've got 58/32. Over 5. But then I need to multiply that by root 3 over 2. And so I get 29/16, because those are both divisible by 2, root 3 over 5. So keep that little pocket right there in your head, because that's going to be useful for our next one. Now, again, like I said, we could totally do this. We could distribute that out and make it happen. But let's look at the semicircle. And what I found is interesting is it doesn't matter if it's an equilateral triangle, a semicircle, a square, a 45, 45, 90, any of those particular things, they're going to end up having this piece of the root equation show up with some variable constant in front, but ultimately you'll notice that it shows up. So we're going to take these semicircles, and I used my ellipse maker, and I feel like this ellipse is a little too strong, so that from here to here is still 27 minus y. But that 27 take away y from here to here is my diameter. So keep in mind, if I divide that by 2, I'm looking at my radius. So remember the area of that triangle is 1/2 pi r squared times a dx. So let's go ahead and do that. My radius, of course, is 27 minus y over 2. 27 minus y, all divided by 2. So it's 1/2 pi r squared dx. And again, we're going to go ahead and go from 0 to 3, and we're going to double that, which is actually very, very convenient because these would cancel. I also noticed that 2 squared right here is a constant of 4, so I'm going to pull that in front. And you're going to notice again, we have 27 minus y squared. But we know that y is 3x squared, right? So I'm going to save a little bit of time by subbing that in there. But we've already done this portion of the math right here a minute ago, and we got 5832 over 5, but it's going to be multiplied by that constant sitting in front of pi over 4. And so we end up, again, this divides in quite nicely to 1,458 pi over 5, because 4 goes into there 1,458 times. So again, the nice thing is if you watch for it, you can end up doing these problems more rapidly. Now, letter C is actually, I think, a little bit more of a straightforward question because there's going to be no subtraction or anything, no craziness. It's just a simple thing that kind of looks like a vase or something like that, okay? So we're going to do pi r squared dy because our little pieces are going in the y direction as I bring them all together. So from here to here is some kind of an x value. And we have one last little thing to do, which is to say, what is x squared? So right here, that's a little bit of a bummer because what I could say is that y divided by 2 is x cubed. Or in other words, x is y over 2 with a cube root on it. So what I need to do is I need to integrate y over 2 raised to the, in fact, I guess it would be, it's a 1/3 power, but it's squared, so it would be 2/3 dy. And y is going from 0 to 5 because it indicates from this region, which started at 0, up until y equals 5. Now, as we do that, that may seem a little bit gross, but it doesn't come out too bad because 2 to the 2/3 power, 2 squared is 4. So this is the cube root of 4, which is a constant. And we're going to integrate y to the 2/3 dy. And okay, nice numbers? No, certainly not nice numbers. Y to the 5/3 with a 3/5 in front from 0 to 5. And we can kind of keep moving our way through this process. And I wrote this down earlier in a nicer version. So I'm going to look and see if I can find out where I wrote it down. As it turns out, this simplifies down to pi over the cube root of 4 times 3/5. And then we end up with this 5 raised to the 5/3 power. 5 raised to the, why did I write y? I meant to write 5. 5 to the 5/3 power. What's a little bit nice is this is 5 to the 1st right here. So we've got pi over the cube root of 4, 5 to the 3/3, and 5 to the 5/3 would cancel and leave 5 to the 2/3. And this is 3/5, but it really doesn't, this is gone actually. because I canceled it out, and we end up with approximately 17.361 units cubed. Okay, no bid. Okay, we got it. This is the precise answer with all of its formality, but this is a pretty reasonable answer when something is quite that gross. But sometimes they do want the full value. So if we go around the y-axis, we're going to have a pi r1 squared minus a pi r2 squared. We've done a few of these things now. So the outer radius is some kind of an x. It is the x curve. And the other one is the linear piece that I'm taking away. So if I am taking x squared is in fact y. And if I'm taking x squared, that is in fact y squared. We're going around the y-axis, so keep in mind as we look through our pieces, this is a washer because we're going to have that center part removed. We are looking at a dy because that is the thickness. And the only other thing that we have to do is we have to figure out where do these things cross. So if y and x are the same, then x equals x squared. And again, doing a little bit of math, which is not particularly difficult, we find out that those two things intersect at x is 0 and 1. X equals 0 and x equals 1. But since y and x are identical, that means we're going from 0 to 1 as well. And so pretty simple value, 1/2 y squared minus cubed. Hey, what do you know? Let's evaluate that nicely from 0 to 1. And we get a very simple pi over 6 because 1/2 times 1 minus 1/3 times 1 is 1/6. And we are out. We're done with problem number 8. All right, see you back.